Exactly.
So last time we finished with this, but we didn't go through the integration of it. And that's going to be pretty important on your next Quizlet. Know how to do that type of integration. So let's go through this. So what should we do next? We have this big long expression. How do we want to go forward?
Simplify and just put a square around it.
Yeah, so we want to simplify this. Okay. So how would you suggest to simplify it?
Multiply the square root of 1 over pi.
Okay, yeah, we can get that. We can pull this out. So we get 1 over pi. What else do we have? Any other things we can pull out from this expression?
Power would just switch to cube.
Z over A naught would be just.
Yeah, we can pull that guy out. If we multiply those two expressions together, what do we get?
1 over
Z over A naught just to the third.
3 over 2.
To the what?
To the third.
Yep. Okay, and now we have to worry about those other integrals. Which one do we want to write first? More of a preference thing, not like a real, one has to be done before the other.
Just do R.
Okay.
R looks nice.
R is going from 0 to what again?
2.
Yep. We got E. Let's combine these terms. What's that going to be then?
-2 R divided by AO.
Yep.
Right, yeah.
-2 R AO, and then we have that R squared we have to worry about. Anything else?
dr.
Nope.
Yep, dr. Times, what's going to come next?
Let's go with
Sine.
theta.
Or d
Yep.
theta, yeah.
Yeah, let's do sine theta. Theta goes from 0 to pi, so sine theta, d theta. And then last, what do we have?
Phi.
Integral from phi to 2 pi.
Yep. Which is probably our favorite integral to do because that one's really easy. Okay, so out of all of this, which of these is the most complex integral that we have to do?
The first one.
Yeah, that first one. Anybody know how to do that off the top of their head?
Yeah, it's easy.
Yeah, super easy, right?
I did it this morning.
It's just for funsies.
That's why I was
Hey,
late. Yeah. I
integral
was just
C.
getting ready.
So, what do you think we want to do for that one?
Integral table.
Yep, go to the table. From table, we got the integral of x squared e to the bx dx is equal to e bx x squared divided by b minus 2x divided by b squared plus 2 divided by b cubed. Okay, in our case, what is b? And what's x?
B is 2 over A.
Yep, we're going to include that negative sign too. So -2 over A. Yep. And what's x in our case?
R.
Yep. I'm sorry, I should have put A naught there. Okay. So these other integrals, we'll deal with them in a minute. Let's just evaluate this guy. Integral R0 to R squared e to the negative R A naught dr. If we use this guy, what is our integral going to become?
2.
E to the negative
Oh,
2 R over A naught.
Yep, times what?
R squared over negative 2. So R squared A naught
Around.
divided by negative 2. Would that be?
Yep. R squared A naught. We got a negative here.
Yeah, negative 2. Yeah.
Okay, next term. Minus,
R squared A naught over 2 squared.
yep. So 2R, and what'd you say, Tara?
Never mind.
Or who said that?
I guess flip it around, just do AO squared divided by 4.
Yep. So that simplifies, right?
Yeah.
What's that going to simplify to?
1/2.
And
Minus, or oh, excuse me, plus. What's going to be the next term?
AO 2 times AO cubed divided by 8. Or negative 8.
Yep, it should be a negative 8. So let's pull that negative out. We'll put it here. And how's this going to simplify?
1
to a 4.
1 to 4.
Yeah, should be a 4. Let me double check and make sure that that's right. Yeah, we'll leave it there. 4. Okay. Okay, so we get that as our expression, and we're going from 0 to 2. Let's look at the integrals for the other parts. We'll do theta first. And then we have phi. Okay, we take the integral of this guy.
cosine.
Yep.
Negative cosine, is it?
Should be negative cosine, right?
Yeah.
Yep.
Negative cosine theta, and we're going from 0 to pi. So if we write that out, it should be negative cosine pi plus cosine of 0, right?
Mm-hmm.
Okay, cosine of pi,
1.
Isn't that negative 1?
yep, that one's negative 1. So we got negative, negative 1, cosine of 0.
1.
For a total of how much?
2.
Okay, d theta. What are we going to get out there?
2 pi minus 0.
2 pi minus 0 or just 2 pi? So now let's plug in all of this stuff back into this expression. So probability will be equal to, we had this stuff out front, so 1 over pi d over a naught to the third, right? Times all this other junk. So we got 2 pi times 2 times e to the negative 2r over a naught, negative r squared a naught 2 minus a r a naught squared over 2 minus a naught cubed over 4. Okay, what we can do now is we can just math this. Things aren't going to cancel out for once to not be 0 or 1. There's actually going to be a numerical value here. So on the Quizlet, you'll want to use either your calculator, or I'll let you use Wolfram Alpha to evaluate like this integral. But what I want you to do is simplify it down as far as you can first. Does that make sense?
Yeah.
So if you do that, the value you should get is 0.981 or 98.1%.
What's Z?
Z, yeah, what's Z in this case?
1.
Yep. So this is equal to 1. Why is it 1?
Because the atomic charge of hydrogen
Yep.
is 1 at the time.
So we're talking about an H atom.
Yeah.
And since the atomic charge is 1, Z is 1. Does that make sense?
Yeah. And then the radius was 2 angstroms.
Yep, R went from 0 to 2. Okay.
And what's A naught again? That's
Some value.
A naught is the Bohr radius that has a
That was
specific
like
value.
0.5 something 8.
Yeah, where is it? Yeah, what'd you say, John?
0.529.
Yeah. 0.5, I think it was 4.
0.529. You're right.
You know.
529 angstrom.
Yep.
But all these things are just constant, so it makes it kind of nice.
Yeah. Exactly. All this junk is just constant, so things cancel out. We could simplify this further too. We could have ditched that pi, gotten rid of that too.
4.
Yep. Okay, any questions about that? No? Okay. So we could look at those probabilities and gauge it that way. But there's also another way to look at the probability of finding an electron. And you guys have most likely seen this in your inorganic chemistry class, or maybe
Also,
even in general chemistry.
With solving this, do units just somehow cancel out?
Yes, the units do cancel out overall.
Okay.
Yes.
So we
Just
don't need to
simply 'cause
convert
we're doing
angstrom
things
to
in angstroms and things, so it's
Oh, yep, angstrom, you don't have to worry about it because eventually it will all cancel out.
okay.
To be
Because
correct.
yeah, it should be unitless. Okay, makes sense.
Because if you look, that's a good question. So R is in what value or what unit again?
Angstroms.
Yep, angstroms. So we have angstroms cubed times angstrom. What's that going to be?
Angstroms to the 4th.
That's
I'm
angstrom
sorry,
cube.
angstrom squared. So this
How
is,
many of those units that are angstrom cube?
so I said angstroms cubed times angstrom.
Yeah.
I should have said angstrom squared times angstrom. What's that get us?
Cube.
Yep. We're going to get an angstrom cubed here. What about for this term?
Same.
Yep. And then finally this guy.
Same.
So, but we want a unitless number, right? So how does this work out to be unitless?
Because the Z over A naught term?
Yep, this guy, we have that A naught term in the bottom, so it's angstroms cubed divided by angstroms cubed. And if you look, everything else is unitless. Yeah. Good question. Okay, so we can evaluate probabilities like we've just done, but sometimes it's just easier graphically to look at a picture and say, this is where the likelihood of the electron is. And to discuss that, we need to talk about radial distribution. We're going to call that, we'll do P of R. So basically what this is, oops, we can focus. You can do it then, yeah. There we go. What this is we look at, we take a function, and if we multiply it by dr, we end up getting the probability of finding the electron at that point. So it's the probability of finding an electron is determined by just taking this distribution function we're going to talk about in a minute and multiplying it by dr. When taking the distribution function which we've given the label P of R, and multiplying by our radial differential. So we should get rid of that. Okay. So for a 1s orbital, you can look these functions up. It'd be P of R is equal to 4 z cubed, a naught cubed, r squared, e to the minus 2 z r a naught. And if we were to plot this guy, we'd have a radial distribution function on our y-axis, so P of R. And we would have our radius. And what we should see is a plot like that. And this approaches 0. It never actually touches 0. We can approximate it to be a 0 though, because it gets really, really tiny. Okay. So now looking at this, remember this is a 1s orbital. What do you think our maximum, or 1s orbital of a hydrogen atom, what do you think our maximum value is going to be, or the maximum, at what radius will the probability be at its max?
The Bohr radius.
Yep, it's the Bohr radius. That's at a naught. And that's the part that it's more likely to be at. Okay. Well, let's ask the question, where does this radial distribution function come from? So where does the radial distribution come from? Okay, we're talking about probabilities, right? So where does probability come from, or how do we determine the probability of finding an electron at a certain point?
Not the equation?
Yep. We could use that. We'll talk about that in a minute, but generally, how have we always done it in this class? We want to find probability.
Normalize. No.
Normal probability equation.
Yep. What's the normal probability equation?
Sin squared
Integral
times
from
psi.
A to B
Yep, psi star, integral a to b, psi star, psi, d tau, right? Okay, we've done this before. For our system, how many integrals do we need?
3.
Yep. 1, 2, 3. Bless you.
Thank you. I coughed, but thanks.
Oh, that was a cough. Sorry. We could put in integration limits. We're going to leave them off because we're lazy for now. And we can break our wave function apart into what two types of functions?
Angular and radial.
Yep, angular and radial. We got the radial part.
Dr. Corky Mom?
Just building those titles, man. N R Y sub L M sub L. Oh no, we're gonna run out of space. Times R squared sine theta d phi dr. Right? Okay, I'm gonna rewrite that to organize it to make it look a little bit better. But we can split these integrals up into their separate parts, right? Tell me the R part, the part that's going to depend on dr.
R squared.
Mm-hmm. Yep, R squared. What else?
And LR.
Yep.
R star and R.
It should technically be R star R, but we know that R doesn't have I's in it, so we're just going to have R squared like that. Next part. We got a double integral in this case. We have y of L m sub L theta phi squared sine theta d phi. And what are the integration limits for this guy again?
0 to pi and 0 to 2 pi.
0 to pi,
Okay.
0 to 2 pi.
Leave some for the rest of us.
What about for this one?
0 to 2.
Not just 2 in this case.
0 to R. Or
Nope,
not
not to
I guess.
R.
Would it be A?
There,
A not maybe? No.
E,
Nope.
C.
Nope.
There's some arbitrary distance.
You could go to some arbitrary distance. That's what you'd have to do to actually evaluate this integral. But what are we going to go to? Or where does the radius end?
Infinity.
Infinity. We're going to infinity, man. There we go. Okay. This looks complicated, but we can simplify this. Anybody have a suggestion on how to simplify this?
The first part's just going to be 1.
This first part is not going to be, oh, like overall infinity. Yeah, you're right. It would be 1.
Yeah.
Doctor?
I don't want to do that yet.
All right.
Where's another spot that will also be 1?
Probably the sine.
Anything dealing with, yeah, I think the sine theta.
Yeah, this
0
whole
to
thing.
pi.
If you remember, we proved that most of these angular momentum functions, along with sine, are normalized. And if we're going across their total integration limits, what should their value be?
1.
Yeah. So this guy is equal to 1. So what we're left over with is R sub m, L, R, squared r squared dr. And that probability function, this guy right here, that's PR. Okay.
So just the inside?
The inside and that r squared, all of that lumped together. We're also, we probably should have gone just some arbitrary number. So that way it didn't equal 1. So we will say from, I don't know, 0 to B.
Wouldn't it just be 2A of naught?
It isn't the most probable, it is the probability.
Ew.
If we are going to see an example where that is A naught. So let's look at an example. Am I okay to move this away?
Yeah.
Okay.
Yeah.
So next, what we're going to do, determine the most probable radius at which an electron will be found when it occupies,
Down a little bit.
oh, yep, sorry. When it occupies a 1s orbital of an H atom. Oh, not a question, it's just a statement. Do it. Sorry, I got excited about writing. So let's look back at our plot. So we already know what the answer is going to be, but we want to prove it mathematically. We need to use this function along here. So let's rewrite that down. So we got P of R is equal to 4Z cubed, A naught cubed, R squared, E to the negative 2, ZR, A naught. Okay. We'll go back to that in a second, but let's just look at this plot for a moment. We already know what the value is, but let's say we didn't, and we were looking at this curve. How would you figure out the maximum of the curve?
Take the derivative.
Yeah, you take the derivative. So we would look at the derivative of that function, and what would we take the derivative with respect to?
R.
Yep, R. So the maximum of this function can be found where dp, dr, and if we're looking at that maximum, what should the value of this be equal to?
0.
Yep. Okay. So now we have a radial distribution function. We know we have to take a derivative, and that derivative has to be equal to 0 to be the maximum. So let's do that. Okay. We take the derivative with respect to r. Does this first part change at all?
No.
No. So that's just a constant. We can pull that out. Okay, so what we're looking at is taking the derivative of r with respect to this portion.
2R.
Mhm.
Chain rule.
2R, what comes next?
And also product rule.
Well,
Yep, it's
yeah, I
pro-
meant from
So then just E.
Mhm.
so then e to the negative 2z r over a naught.
Yep. Good use of the product rule. Now we need the second part. Plus derivative of the second.
So just be the entire top part.
So negative
Oh.
2z over a naught.
Yeah.
Yep. And then what else do we got?
E to
Times
the thing again.
Mhm.
Wait, wouldn't the R go away?
Negative 2z.
Yeah, there
You have to take,
shouldn't be an r.
you have to
No,
take the derivative.
it's just
of,
negative 2z
like,
over a naught.
Oh,
exponent.
yep, my bad. Yep. We got ZR. Ooh, I want to put a squared in there real bad for some reason. All right. Don't know why. Okay, what else do we got? So that's the derivative of the second function. What else do we have to multiply this by?
R squared.
Yeah, that's why I want to write it real bad. Okay, and what's this whole thing equal to?
0.
0. Okay. Let's combine some terms. Let's make this look a little nicer. 4z cubed, a naught cubed. We'll leave that first one alone. Combining stuff here plus, oh shoot, minus 2zr squared a naught e to the minus 2zr.
Oh, wait a second. No, isn't that thing squared? Because technically you'd have to take the derivative and then you multiply by the original function and then take the derivative of the original function as like a whole. So technically you would end up with that E.
So what part are you saying right now?
So the E to the negative 2z R A O, shouldn't we? So when you take the derivative of the top part, you would get what's out in front, and then you would multiply by the original function, and then you would also have to take the derivative of the original function, which would be the same because it's E. Or am I just forgetting like how to
I think we're good so far.
That would be if we were doing a second derivative. I think if you're, because we're only doing one derivative, I think we're okay.
Okay, this has been a little too
Yeah.
long.
Are you saying like, because we did this?
Yeah, because then don't you have to take the derivative of the whole thing? Or am I just misremembering it at this
Losing
point?
it, John, you're losing it.
That's only if there were a second derivative. We'd have to do it again. So we only need one derivative, we're good. Because the way the product rule works is if you take f prime of x, and let's say you have g of x, I don't know, h of x. Oh, actually this is f. So f prime would be g prime derivative of the first times the second plus derivative of the second times the first. Does that make sense?
Yep.
Okay.
Yeah, I was just misremembering.
Yeah. No, we tend to do really complicated stuff, so.
The basics.
Yeah. Yeah, it sucks when you have to go back to the basics because you're like, oh man, I'm in this world of theoretical nonsense. All right, so what do we want to do here? How can we simplify this?
We'd probably pull out
Allowed
an
an
R.
E?
No, never mind. Yeah, we pull out an R, and
So we can pull out
we can
this
pull out
E
that
term.
entire E term.
Well,
Mhm.
2r e to the, yeah, you can pull out that whole first term, honestly.
Yep.
Yep.
We're going to get rid of these guys. It's all 0 on that side, so pull them out. Get rid of them. And we're left over with 2r minus 2zr squared over a naught, right? Is equal to 0. Anything else we can do?
Z can be plugged in as 1, right? Because we're dealing with a hydrogen atom.
Yes, so Z is equal to 1. So now we're left over with 2R minus 2R squared A naught is equal to 0. Anything else we can do?
So we're trying to solve. So A naught, is that still the Bohr radius?
Yep, that's still the Bohr radius. So we're trying to solve for R.
But isn't that equal to A naught right now?
Yeah. Well, no. R can be anything, but we're just trying to figure out the maximum. R will
Okay.
eventually equal A naught. But what can we do to this expression to make it a bit simpler?
So
You could,
anything,
couldn't you take out a 2R?
yeah, we take out a 2R. We get 1 minus R over A naught is equal to 0. So we can just take that over to the other side. We get 1 minus R A naught is equal to 0. We can manipulate this around, right? Let's move that R over A naught to the other side. Then if we solve for R, what's R equal to?
A naught.
A naught.
Yep. Which is the most probable spot to find that electron. Pretty cool. So again, we find something experimental. That's neat.
But isn't like A naught, is that just like a given value, or would, because isn't it like kind of solving itself, but we don't really get a value if we didn't know what A naught is?
Right. But we do know that A naught is a collection of constants.
Okay,
So we still, we would still know what that value is.
gotcha. That's
Just
just
depends.
proving that that's the, okay.
Yep. Okay. We have about 5 minutes left. What we're going to talk about now will not be on the quiz on Friday. Okay?
Good.
Cool. So all you really have to know is the hydrogen atom for that quiz. Are there any questions about this? No? Okay. So we're done with the hydrogen atom. Let's go on to many electron system. Okay, so what we know is we can solve the hydrogen atom, but anything else that has more than one electron, we can't actually solve analytically. Why can't we do that currently? Why can't we do that?
There's too many interactions and you don't know where all of them are.
And when you're saying interactions, what do you mean interactions of?
Bodies.
Between the electron nucleus.
Yep, not electron nucleus.
No.
That one we can do.
Electron-electron interaction causes
Yep.
too many
So the electron-electron interaction, there's too many of them going on, right? So the Schrodinger.
I missed the Schrodinger. We haven't talked about it in a while.
Oh, we'll get back. Don't worry.
I was worried.
It always falls back to it. For a many electron system. And we said is difficult because of all the electron-electron interactions going on. And in our lab, we talked about what type of interactions these are. explicitly with density functional theory. You remember what density functional theory approximates? We have two terms. So we got electronic something and something else.
Is it like the polarization and the? No, I'm thinking of something else.
Sorry, phone's yelling at me. What'd you say, Josh?
So not the polarizability and. If we're looking at density, so we're like the polarizability and there's another one. It's like the.
It relates to polarizability and interactions it can have. One we talked about a lot in inorganic when it came to electron configurations.
Is it correlation?
Yep, one's correlation, so electronic correlation. And that's where all the positions of the electrons depend on one another. And then we also have
exchange, right?
Yep. Which we spent a lot of time discussing what that was in inorganic, and I said it's basically a quantum effect. What we're going to do within the next couple of weeks is actually show mathematically what electronic exchange is. Okay. But in order to solve these types of equations, these systems, currently we have to make some approximations. We are forced to make approximations. So what we're going to do is we're going to go through some of those approximations and explain, like, what do they do and what consequences do they have? Okay. Are there any questions about the material that we covered today?